Welcome, everybody, to this session on Azure SQL Database Serverless. My name is Morgan Oslake. I'm a program manager at Microsoft on the Azure Data Engineering team. In this session, I'd like to discuss what serverless is, then discuss when and how to use it to optimize price and performance, as well as talk a little bit about how it actually works under the hood. Now, when customers begin their journey into Azure SQL PaaS, one of the first decisions is the deployment model that best aligns with their particular application scenario. The managed instance deployment model provides very high degree of application compatibility with on-premise SQL Server implementations, and so makes it a very good choice for lift and shift scenarios. SQL Database provides the greatest amount of management simplicity and is ideally suited for cloud-borne applications. There are two flavors within SQL Database. There's the single database deployment model as well as Elastic Pools. Elastic Pools provide resource sharing across multiple databases for price savings benefits. Serverless in particular is supported in the single database deployment model. But before getting into what serverless is, it's useful to first consider some of the challenges facing developers when price and performance optimizing their workloads. Consider a typical scenario of an IoT application with a centrally managed database that collects rainfall data from thousands of geo-distributed weather stations, as well as providing endpoints for users to connect to it in order to run analytics scenarios as well as generate reports. Now, when the weather is relatively calm, it's easy to imagine that the application usage is relatively low. But when the storm system passes through, the usage on the application can suddenly increase to very high levels. In other words, there's a high correlation between storm activity in this example and workload on the database. But the key point to emphasize here is that the workload demand is unpredictable, both in terms of its amplitude and timing. Now that presents DevOps challenges in terms of how to size the compute for the database in order to achieve your price and performance goals. One option is to provision enough resources to accommodate peak workload demand, but then given this kind of usage pattern of bursty usage followed by relatively low or idle usage periods, this results in wasted resources and ultimately can lead to higher costs. On the other hand, you could decide to provision an amount of compute that aligns with the average usage of the database over time. But then, of course, during peak periods, the application won't have enough resource and can suffer from poor performance. And then finally, if the application is already in the cloud, you can take advantage of cloud elasticity and rescale that database. But the rescaling, especially if it's a homegrown solution, can add to development costs as well as operational complexity. So this is exactly the kind of scenario and problem that serverless is intended to solve. It essentially provides two functionalities. The first functionality is automatic compute scaling over a range that's indexed by a maximum and minimum number of cores that can be configured by the customer and corresponds to a range in memory as well. And whatever the workload demand of the application happens to be, the system relieves the customer of providing that amount of, determining the amount of resources to meet that workload demand and automatically provides the right amount. The second key capability for serverless is its ability to automatically pause and resume. In this case, if the database is idle enough for long enough, then the service will automatically pause the database, put it into a dormant state, and leave it paused until activity returns, at which point the service will then automatically resume the database. Now, in terms of billing, serverless only charges for the amount of compute used on a per second basis, both in terms of CPU and memory consumption. Now, this is to be contrasted, say, with the provision compute tier, where the cost is based on the amount of compute that's allocated, independent of how it's actually used and billed on an hourly basis. Also in serverless, if the database is paused because we've terminated the underlying compute, the only cost that remains is the cost for storage on disk. Otherwise, in terms of PaaS manageability benefits and serverless, they're the same as they are in provision compute. So serverless has built-in high availability. It provides automatic backups and updates. It has built-in machine learning to deliver performance tuning recommendations and various security-related optimizations. When considering whether or not serverless is a good fit for your database, it's crucial to understand its usage pattern. At a high level, if the usage is intermittent and unpredictable, with a relatively lower average compute utilization over time, then serverless tends to be a good fit. So for example, if the database has bursting episodes that are interspersed with periods of lower idle usage, that's the kind of profile that tends to be a good fit for pricing reasons alone. Also, if the database is frequently rescaled, then serverless should almost be considered by default. It's quite possible that serverless will provide uh, better scaling, both in terms of performance as well as price savings. And then finally, if the application or the database is brand new and doesn't have any usage history, then serverless can often be a good starting point. It can reduce, for example, some of the burden in performance testing, which can be quite complicated and involve attempting to assess the usage profile for the database and simulate that usage profile, and can be very time consuming and error prone. So serverless can often be a good fit just by deploying the database into some high level of cores and letting the service take care of all of that sizing for you. If it later turns out, for whatever reason, that serverless isn't a good fit, then it can easily be moved over into the provision compute tier. There's a very high degree of mobility for serverless databases, both in terms of coming into serverless as well as exiting serverless. Serverless isn't a panacea, though. It's not necessarily appropriate for every kind of pattern. There are certain anti-patterns that you should be aware of. If the usage is more regular and steady, predictable, with a higher average compute utilization over time, and we'll make these notions of lower and higher compute utilization more precise a little bit later in the session. If this is true, then provision compute tends to be a better fit. Also, because at its core, serverless is a rescaling solution, it presents some performance trade-offs to take into consideration. There are performance trade-offs related to scaling while it's online, as well as resuming after it's been paused, that center around the system or the service constantly allocating and deallocating resources. And after sort of these lower idle usage periods, the compute for the database needing to take some time to warm up again. which in a sense represents a form of performance penalty. And then finally, if the application has multiple databases, say tens, hundreds, or even thousands of databases, like a lot of SaaS ISVs do, then elastic pools tend to provide better price optimization opportunities. They provide, better compression of usage per unit of compute. Onboarding into serverless is straightforward. Uh, in the case of creating new databases, here what I've shown is a PowerShell commandlet, and I've highlighted the 4 parameters that are unique to serverless. In yellow, there's the compute model, and then specifying the min-max number of cores, as well as the auto pause delay, as we've just discussed. Otherwise, the signature on this API is just the same as it would be for provisioning compute, and the same would be true if I presented a code snippet from CLI or REST. Same goes for existing databases. To move an existing database into serverless is equally straightforward, essentially the same API signature. Of course, the verb changes in this example from new to set. It's also worth pointing out that no application rewrite is required when going into serverless. However, if the database intends to be enabled for pause and resume, then it's crucial that the application have connection retry logic built into it. So with that, I'd like to first demonstrate onboarding into serverless. So here what I'm showing is a logical server in the Azure portal that contains 6 databases. Many of them are serverless databases. Some of them are paused. But what I'd like to do here is create a new serverless database. So I'll click the button called Create Database. This will bring up a new page that is largely pre-filled with database metadata. So all I really need to do at this point is enter the database name. Let's call it MyDB, and click Configure Database. And you can see here it defaults to the general purpose service tier and presents choices to create in provision, compute, or serverless. So I'll click the serverless tile. And then I'm presented with these 3 serverless configuration options that we've just discussed: the maximum number of cores, the min number of cores, and the auto pause delay. So I can adjust the maximum number of cores that I want my database to be able to scale to, all the way up to 40 cores. And I can also adjust the minimum number of cores that I don't want the service to ever scale my database below while it's online. And then finally, I can make adjustments to the auto pause delay. Here it's defaulted to 1 hour, but suppose that my application, I don't want my users of my application to sort of suffer from the performance penalty of compute warm up after pausing and resuming. So I may want to extend the length of time, say, to a little bit more than 1 hour. That ensures that the database doesn't pause, for example, during the lunch hour of the work week, but still benefit from being able to pause and resume at night and on the weekends. Now, if my database is particularly sensitive to the performance impact from compute warm up, then you can disable auto pause altogether, and still benefit from the ability of the database to automatically scale over this compute range and just be billed for the amount of compute that it uses on a per second basis. And then finally, I just hit apply, and within a matter of a minute or so, the database is created, and I'm able to run queries against it. Now, when we set out to design serverless, we wanted to pay special attention to the relationship between memory and CPU usage for any given database. So what I'm showing here is a scatter plot, which is showing the usage of databases both in terms of memory and CPU over a 1-week period. So each point in the scatter plot represents one database and its usage over a 1-week period. Despite how it looks, there are hundreds of thousands of databases actually represented in the scatter plot, which were basically samples taken across a variety of data centers around the world of customer production workloads. Now you can see, for example, that some databases may consume quite a bit of memory, but a little CPU, whereas conversely, other databases may consume a lot of CPU and a little bit of memory, and various combinations of usage in between. So the key point to emphasize here is that the relationship between CPU consumption and memory consumption can be fairly weak. These can be resources that behave independently of each other. And so we took that to heart in the design of serverless. So here, I have, in my example, I have a serverless database that's configured with a max of 16 cores and a min of 2 cores, corresponding to a memory range from 6 to 48 gigs. So it could be that this serverless database at one point in time is performing, say, a table scan, and therefore loading a lot of data into its buffer pool, which may require a lot of memory, but very little CPU. Then, as time passes, that same database may evolve in its orientation to become much more computationally intensive, and perhaps require 16 cores and much less memory. So the key point to emphasize here is that for a given serverless database, whatever combination of CPU and memory resources are required are actually delivered by the service. Another way to say this is that the memory to vCore ratio in serverless is dynamically adaptive based on usage and ranges all the way up to 24 gigabytes per one core, which is quite a wide range. Now, in terms of a scale-up latency, suppose, for example, that at one moment in time, my database is utilizing 2 cores, and then in the next moment suddenly needs to burst to 16 cores. Serverless tends to be able to accommodate that rescaling operation very quickly, usually in under 1 second, although there can be occasions where that scale-up time is on the order of a few minutes if load balancing is required internally within the service. And we'll talk a little bit more about that later. But for the most part, most of the time, the scaling in serverless is virtually instantaneous. Now, if you compare that to scaling with provision compute, it's quite a different world. In provision of compute, of course, the burden shifts to the customer to identify up front the amount of compute that they require for their workload. So suppose I've determined that my database needs 2 cores. Then on generation 5 hardware, that database will be allocated about 10 gigs. Now, one of the advantages of provision compute is that those 2 cores and those 10 gigs will be continuously allocated without interruption. There's no reclaiming reallocation of resources under the hood. You can think of provision compute as providing your application pristine performance dial tone. The flip side of the coin is that those resources are being charged whether or not they're actually being used. Now, if the same database at some later point in time becomes overutilized, the burden again shifts to the customer to determine the compute, the number of cores, the amount of memory that need to be allocated to accommodate that increase in activity. This, of course, can be complicated. It involves, first of all, defining the resources to analyze, then defining measuring the utilizations of those resources, defining a trigger point. And once all that's been determined, uh, uh, then identifying the specific amount of compute to scale to can be equally, if not more, challenging. And then finally, as sort of the third step in provision compute, the actual initiation of the scaling operation itself, which can take at least a few minutes, if not in some cases a few hours, depending on the particular service tier. And then at the end of that rescaling operation, memory is reset and connections are always dropped, representing, of course, a brief disruption to availability. Now, this can happen in the serverless compute tier as well, but only occasionally if this load balancing becomes required. Otherwise, not only is the scaling speed virtually instantaneous, but the impact to performance and availability is also virtually imperceptible. So with that, I'd like next to demonstrate autoscaling in serverless. So here I've pre-created a database, and I can see by its service objective that it's in the general purpose tier. S stands for serverless on generation 5 hardware with 8 max V cores configured. And what I'd like to do is run a couple of expensive queries against that database. So each of these queries are selecting system objects, then materializing a large table and performing a nested loop join. So these are very CPU intensive operations that are now running concurrently against that serverless database. And so in order to demonstrate how quickly this database is able to scale up to the 8 cores that it's allowed to, I can look at the DMV for DB resource stats, which reports on utilization across key metrics like CPU. So what I can see here is that my query started, say, roughly at 10 minutes and 21 seconds. And then by 10 minutes and 43 seconds, so about 23, 22 seconds later, it was consuming virtually 100% of all 8 cores. So this database went from essentially idle usage to using all 8 cores in a matter of about 20 seconds or so, according to this telemetry. Now, this database probably scaled up much more quickly than that. Here, we're only limited by the resolution in the telemetry of this DMV, which is collecting and reporting on usage once every 15 seconds. So how does memory management work in serverless? Well, first, let's talk about the various pockets of memory in SQL. So SQL has cache memory as well as query grants. Query grants are allocated to run queries and then deallocated when those queries complete. So the allocation of memory for grants tends to more or less follow the usage pattern of the database. But cache is different. Cache here, of course, includes things like buffer pool, which contain the database data pages of the database, column store cache entries, precompiled plans for faster query execution. Lots of different caches form the overall cache memory in SQL. And once those caches become hydrated, once that cache memory grows, it tends never to be released, unless, of course, there happens to be actual memory pressure. So cache stays high, and for good reason. If at some later point in time, after a database sort of starts to get busy again, it needs data, then rather than having to fetch that data from disk, it can quickly retrieve it from the buffer pool. So there's performance advantages, of course, in having the cache memory run high. But this presents a challenge in the serverless paradigm because not only is CPU charged, but so is memory. So in serverless, what we do instead is reclaim cache memory when usage on the database becomes low enough or long enough. So how does cache reclamation work in serverless? Um, Essentially, we earmark every entry in cache as either being hot or cold. So it's earmarked as hot if it was recently accessed, and earmarked as cold if it was less recently accessed. And then on a periodic basis, we calculate the total size of all of the hot cache entries and then compare that relative to the size of the total cache itself. So we're taking sort of, in a sense, the ratio of hot cache entries in terms of their size to the total cache size, the active cache utilization, in other words. And if that utilization of active cache is below threshold, if it's low enough for long enough, then we take an action to reduce the SQL memory target. The process of reducing that SQL memory target will, of course, cause page evictions, cache entry evictions to occur. But the cache entries that are evicted aren't necessarily the oldest entries. They're instead the entries that are least costly to rehydrate. So, for example, um, if I have a buffer pool page that was last accessed more recently than, say, a planned cache entry, it's quite possible that the buffer pool page will still be evicted first before the planned cache entry. And the reason for this is because recompiling of the plan could be a much more expensive operation than simply doing an IO to fetch a page from disk for the buffer pool. So this is another sort of phase in the serverless workflow where the service is attempting to strike the right balance, both in terms of price and performance. Pausing and resuming, how does this work? So while the database is online, the service is constantly analyzing its usage history. Um, Two key metrics that it's looking at in terms of making the decision whether or not to pause are the number of sessions and the CPU usage by the user workload. So if the total number of sessions is identically zero and the CPU usage is also identically zero, for the length of time as specified by the auto pause delay, which was the configurable by the customer, if both those conditions are true for that length of time, then the service will initiate the pausing operation. One of the critical steps in the pausing workflow is to take tail log backups to ensure an orderly shutdown of the database. This is followed by detaching the database files, then terminating the underlying SQL instance, and then finally stopping the billing for compute. The latency for that entire pausing workflow, it's variable. It tends to be around 1 minute, but it can range up to as long as 10 minutes. Primarily, the variability is due to taking the tail log backups. Then while the database is paused, it remains paused indefinitely unless the workload activity returns to the database. Now, generally, this means that the customer is re-engaging the database. There are more rare cases, for example, during, say, a service update, where the service will automatically resume a database. in order to apply a patch, and then the database will pause again. For the most part, it remains paused until the next login is received. Once that login is received, billing for compute resumes, the SQL instance is launched, and the database files are attached to the instance, at which point the database is then online. The period of time or the latency for the resume operation, which in some sense is more critical for performance, whereas the pausing latency is more critical for price savings. The resuming latency tends to be around 1 minute as well. It can be as short as 30 seconds, and there is some variability there also. So now that we've talked about what serverless is, we've talked about a little bit about how it works. It's useful to overlay that understanding on its architecture and then connect that back to the customer performance experience. So serverless is a three-tiered architecture. There's a control plane, which has a gateway service that's responsible for managing connectivity. There's a management service that handles DDL operations like create, alter, and drop. And then sitting below that is the data plane, which contains tenant rings, which are collections of physical machines that provide compute for the databases. And then separate from the compute machines is a storage plane, which contains the database files that are located on remote solid-state disks. So now let's suppose that the database is in the pause state, and let's follow its journey across this architecture. So the first thing that will occur is that the database will open a connection. That connection will be received by the gateway. That first connection attempt will fail if the database again is paused, which is why it's very important for the application to have connection retry logic implemented. Then on a subsequent connection attempt, the gateway will authenticate the client and then pass control over to the management service, which works in cooperation with the service fabric to identify a machine, well, a ring, and then a machine within a ring that has sufficient capacity to relaunch that serverless SQL instance. The initialization of that serverless SQL instance as one of its key steps, as we discussed before, involves attaching these remotely stored database files. And then at the conclusion of that resuming process, the database is back online and able to process queries. Now, the machine contains a service called RG Manager, which performs continuous surveillance of machine utilization, as well as utilization from individual databases hosted by the machine. And if it detects any kind of localized bottleneck, then it will attempt to resolve it. So, for example, if there are two, say, serverless databases sharing the same subset of cores, then and those cores, that subset of cores that are being shared, become overutilized, RG Manager detects that condition, will identify a cooler subset of cores on the same machine that it can then reaffinitize one of the serverless workloads to. And that reaffinitization motion is extremely quick. It's on the order of microseconds and a virtually imperceptible impact in terms of performance to the customer's workload. Now, there can be cases where the overall machine itself is overutilized. In that case, the service fabric re-enters the picture and identifies a different machine in the same tenant ring that has sufficient capacity to accommodate that rescaling operation for the serverless database, and will then orchestrate repositioning that database from one machine to the other. It's that load balancing motion that I touched on earlier that from a customer experience perspective can mean that the rescaling operation is ongoing for a few minutes and results in drop connections at its conclusion. But also, as I said before, that's a much more rare occurrence. Most of the time, the rescaling of a serverless database can be satisfied by the resources on the same machine um, and done rather quickly, virtually instantaneously, with virtually imperceptible customer performance impact. So, how to think about pricing in serverless? It's useful to compare it against provision compute, and then sort of come up with a rule of thumb as to whether or not when serverless is a better fit. So, to do this, let's think about the unit price, the compute unit price for both. That is to say, the cost for one core, let's say for 1 hour. In the provision compute tier, and of course it varies by region to some extent, but roughly in the provision compute tier, the retail list price for one core on Gen 5 hardware is about 25 cents per hour. Whereas in serverless, the unit price for one core is roughly twice as much, 52 cents for 1 hour. But the key here is that it's 52 cents for 1 hour and serverless if the database is using that core for the full hour. But if it's not, if it's say using it for less time, say half as much time or 30 minutes, then the cost of that one core over that length of time is half as much. It's about 25 cents or on par with provision compute. In other words, the rule of thumb is if the average usage of a serverless database is under 50%, both in terms of CPU and memory, then serverless tends to be a better pricing fit than provision compute. So how exactly is billing calculated? At a high level, uh, think of serverless as being charged for the high watermark between CPU consumption and memory consumption for each second in time. So the way this is done is that, say, for a given second, the service will assess how many cores are being used in terms of CPU and how much memory is being used, and take the larger of those two quantities to determine the compute cost for that 1 second of time. Now, of course, the question is, how do you compare the usage of memory to CPU? They're different resources with different units. So we essentially just numerically rescale or convert memory consumption in terms of gigabytes into memory consumption as represented by cores based on this rescaling ratio of 3 gigabytes per core. So for example, if at 1 second in time, the database is using one core and let's say 6 gigs, then we'll take that 6 gigs of memory consumption divided by 3 gigs per core. That translates into 2 cores based on memory usage. Compare that against the 1 core of usage based on CPU. 2 cores is more than 1 core. So 2 cores will be billed for that 1 second, and that's due to memory. Now, at the next second in time, the usage pattern can change, and it could be that CPU dominates the cost, in which case it's the CPU that will be determine the bill for that 1 second instead of memory. And so that leads to a certain number of vCore seconds that accumulate over time to determine the compute bill. So you take those number of vCore seconds and multiply them by the unit cost or the dollars per vCore second, and that will produce a total cost for compute to which storage is billed to determine the total bill for the database. So with that, now I'd like to demonstrate some of the price savings that are possible with serverless. So here I'm showing the Azure portal again. It has a database that's been configured in serverless with a maximum of 16 vCores. And you can see in the chart in the lower left that its compute usage over time is rather bursty. There are 2 bursting episodes where the compute usage was 100% of all 16 cores. And then the other points in time, the usage was lower or essentially idle. You can also see how this compute usage tracks quite closely with the chart on the right, which is displaying the number of vCore seconds that are billed. So if I want to determine the total compute cost for this database, let's say over a 24-hour period, I just need to aggregate the total number of vCore seconds over that length of time. And that's represented by this metric in the lower right-hand corner. 200 and roughly 81,000 vCore seconds have been billed over a 24-hour period. So if I input 281,280 vCore seconds, there we go. So in other words, if I have 281,000 vCore seconds, and I know the compute unit price, which is some dollars per vCore second, fractions of a penny, and I compute the product of those 2 quantities, I'll get the total serverless compute cost, which is just north of $40. Now, the key point here is if I compare that against the cost in the provision compute tier for 16 cores, that cost comes to, based on retail pricing, almost $100. So here, the price savings with serverless is a little bit more than 50% relative to provision compute. Now, it was crucial in this example that the usage pattern of the database had this bursty profile with relatively lower idle usage periods in between. If, on the other hand, this database were utilized consistently at a high level of compute over the same time period, then it's quite likely that the pricing equation would begin to shift more favorably from serverless into the direction of provision compute. In terms of roadmap, we are working on support for hyperscale. Right now, serverless is only supported in the general purpose tier. So there are plenty of workloads that require more I/O performance or higher storage capacity than the general purpose tier can provide. We'd also like to keep pushing the limits on the compute maximums. We recently updated the maximum from 16 cores this summer up to 40 cores, as we saw, and we'd like to keep pushing those boundaries further. We're making investments, more investments in pausing and resuming. For example, we'd like to lower the auto pause delay from the current lower bound of 1 hour to something on the order of minutes. And the reason for this is to give databases with the lower auto pause delay more opportunities to go through pausing and resuming cycles, which can translate into even more cost savings. We're making improvements in the connectivity that will benefit serverless. For example, we are building connection retry logic into SQL client libraries to remove that programming burden from developers that are interested in consuming, pausing, and resuming in serverless. And then finally, we want to expand sort of the range of HA choices in serverless to include availability zones. In summary, Azure SQL Database Serverless is price and performance optimized for single database workloads with intermittent and unpredictable usage. And it achieves this by automatically scaling compute, and optionally automatically pausing and resuming, and then billing just for the amount of compute used on a per second basis. So for more information, we'd invite you to visit aka.ms/SQLDB_serverless. And with that, I'd like to thank you once again for joining this session.